Look up. No, really. The next time you're outside on a clear night, away from the city lights, stop whatever you're doing and look up. What do you see? Points of light. Thousands of them scattered across a velvet darkness. Your brain, that magnificent pattern-seeking machine, immediately tells you a story. It tells you these lights are permanent, eternal, that they have always been there and always will be. But here is the thing. Your brain is lying to you. It's one of the grandest illusions the universe has ever performed, because those stars, every single one of them, was born. They live their lives burning, changing, evolving over timescales that make human civilization look like a mayfly's afternoon. And they die. Some die quietly, a slow fade into darkness. Others go out screaming. Explosions so violent, so unimaginably powerful, that for a brief moment, just a few weeks, a single dying star can outshine an entire galaxy. 100 billion other stars, and one death outshines them all. The night sky is not a photograph. It is a battlefield, a nursery, a graveyard, all at once. Right now, as you read these words, stars are being born in vast clouds of gas scattered across our galaxy. And right now, somewhere in the cosmos, a star is collapsing, its core crushing down into something so dense that a teaspoon of it would weigh more than Mount Everest. The universe is alive with stellar birth and stellar death, an endless cycle. 14 billion years and counting. And here is what I find most extraordinary. You are part of this story, not metaphorically, not poetically, not in some vague spiritual sense. Literally. Look at your hand. Go on, look at it. That hand is made of atoms. Carbon atoms in your skin, calcium in the bones underneath, iron in the blood flowing through the veins. Now here is the question. Where did those atoms come from? Because here is the thing, they weren't always there. When the universe began 13.8 billion years ago, there was no carbon, no oxygen, no iron, no calcium, just hydrogen, mostly, the simplest element, one proton, one electron, nothing else. So where did the carbon come from? Where did the iron in your blood originate? Inside a star that died before our solar system even existed. The carbon atoms that form the backbone of your DNA, every single one of them were forged in the heart of a dying star, in a nuclear furnace burning at 100 million degrees. The oxygen you're breathing right now, the oxygen keeping you alive at this very instant, was created in the core of a massive star that exploded billions of years ago, scattering its guts across light years of empty space. The iron in your blood that was made in the final seconds of a supernova, a cosmic catastrophe, a star tearing itself apart. You are not observing the universe. You are made of it. You are stardust that woke up. You are what happens when hydrogen, given enough time and the right conditions, starts asking questions about itself. So understanding the life cycle of stars isn't just abstract astrophysics. It isn't just numbers and equations on a blackboard. It's understanding your own ancestry, your own origin story, where you came from at the most fundamental level possible. Let's begin where all stars begin, in the cold, in the dark, in the emptiest places in the universe. If you could travel between the stars, if you could somehow cross those vast gulfs of nothingness that separate one sun from another, you would discover something surprising. Space isn't entirely empty. Scattered throughout our galaxy, hidden in the darkness, are enormous clouds of gas and dust. We call them nebulae. These are the stellar nurseries, the maternity wards of the cosmos. And they are colossal. The Orion Nebula, you can see it with your naked eye. That fuzzy patch in Orion's sword stretches 24 light years across. Think about that. Light, travelling at 300,000 kilometers per second, takes 24 years to cross it. The Eagle Nebula, home to the famous Pillars of Creation, spans 70 light years. These structures are so vast that human intuition simply breaks. But here is the paradox. These nurseries, these birthplaces of the hottest objects in the universe, are cold, unimaginably cold. The temperature inside a typical stellar nursery hovers around 10 to 20 Kelvin. That's minus 250 degrees Celsius. Colder than anywhere on Earth. Colder than the darkest Antarctic winter. And the gas, it's thin. Thinner than the best vacuum we can create in any laboratory on the planet. If you were floating inside one of these nebulae, you wouldn't even notice. You'd look around and see nothing. Just darkness. Just cold. Just atoms of hydrogen drifting aimlessly through the void, separated by miles of empty space. A ghost town of potential. So how? How does a cloud of cold, diffuse gas spread across dozens of light years become a star? How does it become an object with a core temperature of 15 million degrees? The answer is a single word: gravity. Gravity is patient. I want you to understand this, really feel it, because it's important. Gravity doesn't rush. It doesn't hurry. It just waits. In a nebula, every atom of hydrogen exerts a tiny gravitational pull on every other atom, infinitesimally small. Under normal circumstances, this pull is far too weak to overcome the random thermal motions of the atoms. Even at those frigid temperatures, the cloud just sits there, silent, still, for millions of years. But then something happens. Maybe a shock wave from a nearby supernova ripples through the cloud. Maybe the galaxy's rotation causes a disturbance. Maybe there's just a random fluctuation, a region that happens by pure chance to be slightly denser than its neighbours. Whatever the trigger, the balance tips. And once it tips, once gravity gets a foothold, it cannot be stopped. The denser region pulls in more gas. More gas means more mass. More mass means stronger gravity. Stronger gravity pulls in more gas. It's a runaway process, a feedback loop, an avalanche. This is gravitational collapse. And it is the first step in the birth of every star that has ever existed or ever will exist in the entire universe. Now, I want you to appreciate the time scales here. A region of nebula might take hundreds of thousands of years to collapse, sometimes millions. By human standards, that's an eternity. Our entire recorded history, every civilization, every war, every love story, every book ever written fits into maybe 5,000 years. The collapse of a stellar nursery takes 100 times longer than that. But by cosmic standards, it's the blink of an eye. As the gas collapses, something beautiful happens. It begins to spin. This isn't because some cosmic hand set it spinning. It's physics. Conservation of angular momentum, one of the most fundamental principles in the universe. Any slight rotation the original cloud had, however tiny, gets amplified as the cloud shrinks. Think of an ice skater. Arms out wide, spinning slowly. Now she pulls her arms in tight against her body. What happens? She spins faster. Same principle. As the cloud collapses, it spins faster and faster. And as it spins, it flattens. It becomes a disk, a swirling disk of gas and dust, with most of the mass concentrated at the center. That central concentration, that's what will become the star. The disk around it, that will become planets. Moons, asteroids, comets. Our entire solar system began exactly this way. A swirling disk around a young sun 4.5 billion years ago. At the center of this disk, the gas gets denser and denser. And as it compresses, something fundamental happens. It heats up. This is basic thermodynamics. You compress a gas, you force the atoms closer together. They collide more frequently, more violently. Those collisions become heat. If you've ever used a bicycle pump and felt it grow warm in your hands, you've experienced this. The center of the collapsing cloud begins to glow. Not from nuclear fusion, not yet, just from the heat of compression. This glowing ball of hot gas is called a protostar. It's not a star yet, it's just getting started. And as the protostar keeps contracting, the temperature keeps rising thousands of degrees, tens of thousands, hundreds of thousands. The atoms are moving so fast now that electrons get stripped away. The gas becomes plasma, a sea of naked atomic nuclei and free electrons careening around at tremendous speeds. Still, the collapse continues. Still, the temperature climbs. 1 million degrees, 5 million, 10 million. And then something extraordinary happens at 10 million degrees. The protons, the nuclei of hydrogen atoms, are moving so fast now, with so much energy, that when they collide, they can overcome something that should be impossible to overcome. You see, protons are positively charged, and positive charges repel each other. Under normal circumstances, two protons approaching each other would be pushed apart long before they got close enough to touch. The electromagnetic force, the same force that keeps atoms apart, that stops you from falling through the floor, is screaming at them to stay away from each other. But at 10 million degrees, some protons are moving fast enough to ignore that scream. They get close enough. And when they do, a different force takes over. The strong nuclear force, the most powerful force in nature. It snaps shut like a trap. It binds them together. Hydrogen becomes helium, and a tiny amount of mass, just a fraction of a percent, vanishes. Where does it go? It becomes energy. This is Einstein's equation made real. E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is enormous. Square it, and it becomes colossal. So even a tiny bit of mass converted to energy releases a tremendous amount of power. This is the moment. This is when a star is truly born. When nuclear fusion ignites in the core, the protostar becomes a star. A new sun blazes into existence, a new light in the darkness. And something remarkable happens in that moment. The energy from fusion creates an outward pressure, a force pushing against the inward crush of gravity. And when the fusion rate becomes high enough, this outward pressure exactly balances gravity's inward pull. The star stops collapsing. It stabilizes. Gravity is pulling in, trying to crush the star out of existence. Nuclear fire is pushing out, trying to blow the star apart. And they reach a stalemate, a perfect, precarious balance. We call it hydrostatic equilibrium. Think about that. A star is essentially a controlled thermonuclear explosion, a vast hydrogen bomb that has been burning steadily for billions of years, held together by its own gravity, neither exploding nor imploding, just existing in perfect balance. The violence is so total, so complete, that it becomes peace. This balanced state, this equilibrium, is where most stars spend most of their lives. We call it the main sequence. Our sun is here right now, has been for 4.5 billion years, will be for another 5 billion or so. Every second, our sun converts 4 million tons of mass into pure energy. 4 million tons, vanishing, transformed into light and heat. The warmth on your face on a summer day, the energy that drives the weather, the light that allows plants to photosynthesize, and through them allows you to exist. All of it comes from mass being annihilated at the core of our star. 4 million tons every second. And yet the sun is so massive, 2,000 trillion tons, that it can keep this up for billions of years without running low. But stars are not all the same. They come in tremendous variety. Blue giants, burning hot and bright, living fast and dying young. Red dwarfs, cool and dim, so efficient with their fuel that they'll still be burning when the universe is 100 times its current age. Yellow stars, like our sun, somewhere in the middle. The rule is simple, and it is cruel. The more massive a star, the shorter its life. You would think it would be the opposite. More mass means more fuel, right? More fuel should mean longer life. But more mass also means stronger gravity. And stronger gravity means the core must burn hotter, faster, more furiously, just to keep from collapsing. A star 10 times the mass of the sun doesn't live 10 times as long. It lives 1,000th as long, a few million years instead of 10 billion. The brightest stars in the sky, the blue-white beacons, are the young ones, the mayflies of the cosmos. They burn through their fuel with reckless abandon, blazing across the universe like meteors, then exploding and dying before their dimmer, smaller neighbours have barely started. Meanwhile, a red dwarf, a tiny, dim ember of a star, perhaps 1/10 the mass of the sun, burns so slowly, so efficiently, that it will keep shining for trillions of years, long after every other star has gone dark. There's a lesson in there somewhere about living fast versus living long. I'll let you decide what it means. While a star is on the main sequence, burning hydrogen in its core, something fascinating is happening, something most people never think about. The energy generated at the core has to get to the surface somehow, but it doesn't just stream outward. It can't. The interior of a star is opaque, packed with particles that absorb and re-emit radiation constantly. A photon, a particle of light, born in the sun's core, might travel only a few millimeters before being absorbed by an atom. That atom then re-emits another photon in a random direction. That photon travels a few more millimeters before being absorbed again, and so on, and so on. A random walk, a drunken stumble through the stellar interior. How long does it take for energy generated in the core to reach the surface? Estimates vary, but the answer is somewhere between 10,000 and 100,000 years. Let that sink in. The sunlight warming your face right now, that energy was generated in the sun's core during the last ice age, perhaps earlier. It has been bouncing around inside the sun, slowly working its way outward for longer than human civilization has existed. 8 minutes from the sun's surface to Earth, 10,000 years from the core to the surface. Time moves differently inside a star. but nothing lasts forever, not even stars. For billions of years, hydrogen fusion in the core has been fighting gravity's endless pull, winning even, maintaining that perfect balance. But fusion has a cost. It consumes hydrogen, and it produces ash, helium, the ash of hydrogen fusion. Slowly, inexorably, helium accumulates in the core, like cinders building up in a furnace, and helium doesn't fuse, not at these temperatures. Helium nuclei carry twice the positive charge of hydrogen, so the electrical repulsion between them is 4 times stronger. To fuse helium, you need temperatures far higher than 15 million degrees. You need 100 million degrees. The core can't get that hot, not yet. So the helium just sits there, inert, dead weight, accumulating, choking the furnace, and without fusion to generate outward pressure, the core begins to shrink. This is the moment the clock starts ticking. As the core contracts, it heats up, and this heat ignites something new, a shell of hydrogen around the core, hydrogen that wasn't quite hot enough to fuse before. The star develops a hydrogen-burning shell wrapped around an inert helium heart. This shell burning produces more energy than the core ever did, much more. And all that energy has to go somewhere. It pushes outward. The outer layers of the star expand, and as they expand, they cool. The star is becoming a red giant. For a star like our Sun, this transformation is apocalyptic during its main sequence life. The Sun has a diameter of about 1.4 million kilometers, respectable. When it becomes a red giant, 5 billion years from now, it will swell to perhaps 200 times that diameter. Its outer atmosphere will push past the orbit of Mercury, past the orbit of Venus, and possibly, probably, past the orbit of Earth. Whether Earth gets swallowed depends on details we can't yet predict. The Sun will lose mass as it expands, which will cause Earth's orbit to migrate outward. But will it migrate fast enough? Maybe, maybe not. Either way, it won't matter. Long before the Sun's atmosphere reaches us, Earth will be transformed. The oceans will boil away. The atmosphere will be stripped. Every trace of life, every book, every building, every memory of everything humans ever did or thought or felt, all of it will be erased. The red giant sun will be luminous, thousands of times brighter than today. But spread across such an enormous surface, each square meter will actually be cooler than the current sun. The surface will glow a deep, angry red. Red giants aren't red because they're hot. They're red because they're dying. But the core hasn't given up yet. As the star expands outward, the core keeps contracting inward, heating up. The helium ash accumulates, gets denser, hotter. After perhaps 1 billion years as a red giant, something dramatic happens. The core temperature hits 100 million degrees, and at that temperature, helium can fuse. The process is called the triple alpha process, and it's remarkable: 3 helium nuclei, 3 alpha particles smashed together to form 1 carbon nucleus. But there's a problem. If you fuse 2 helium nuclei, you get beryllium-8, and beryllium-8 is fantastically unstable. It falls apart in about, well, let me put it this way. Write down a decimal point, then write 16 zeros, then write the number 1. That's how many seconds beryllium-8 exists before disintegrating. That's not a lot of time. But in the insane conditions of a red giant's core, beryllium-8 is being produced so frequently that even though each nucleus exists for only a trillionth of a second, there's always some beryllium-8 present. And occasionally, just occasionally, a third helium nucleus slams into a beryllium-8 before it can decay. Carbon is born. This is where the carbon in your body came from. This exact process. The triple alpha reaction occurring in the cores of dying stars billions of years ago. Sometimes, before the carbon can escape, it captures a fourth helium nucleus and becomes oxygen. This is where the oxygen you're breathing came from. Every breath you take connects you to dying stars. In stars like the sun, the ignition of helium is violent. The core has become so dense, so degenerate, meaning the electrons are packed so tightly that quantum mechanics takes over, that when helium fusion begins, it triggers what we call a helium flash. Temperature rises, fusion speeds up. More energy releases. Temperature rises more. Normally, a star would expand in response, cool down, regulate itself. But in a degenerate core, that safety valve doesn't work. The fusion rate skyrockets. In just a few seconds, the core releases as much energy as the entire galaxy produces in the same time. It's an explosion inside the star, but you wouldn't see anything from outside. All that energy goes into lifting the degeneracy, allowing the core to expand and return to normal behavior. The star survives, settles into a new equilibrium, fusing helium into carbon in the core, hydrogen into helium in a shell around it, but not for long. The helium burns faster than the hydrogen did. 100 million years instead of billions. And then history repeats itself. The helium runs out. A carbon-oxygen core forms, inert, unable to fuse. The core contracts, heats up. Helium shell burning ignites. The star expands again. For a star like the sun, this is the beginning of the end. The sun doesn't have enough mass to take fusion any further. Carbon fusion requires 600 million degrees. Oxygen fusion requires over 1 billion. The sun's core will never get that hot. So what happens instead is beautiful in a sad way. The outer layers become unstable. Thermal pulses cause the star to pulsate, expanding and contracting over months or years. With each pulsation, the star sheds more of its atmosphere into space. Stellar winds carry gas outward, gradually stripping the star naked. Over 100,000 years, the star loses half its remaining mass. The shed material forms an expanding shell around the dying star, illuminated by the increasingly exposed, increasingly hot core. We call these structures planetary nebulae. They have nothing to do with planets. The name is a historical accident, but they are among the most beautiful objects in the cosmos. The Ring Nebula, the Cat's Eye, the Helix, ghostly shells of glowing gas, the final breaths of dying stars, material being returned to the cosmos to become part of future generations of stars and planets. And at the center of each planetary nebula, the core, a ball of carbon and oxygen, perhaps the mass of the sun compressed into a volume the size of Earth. This is a white dwarf. White dwarfs are extraordinary. A teaspoon of white dwarf material would weigh several tons on Earth. The atoms are packed so tight that electrons have been squeezed out of their orbits, forming a degenerate sea throughout the star. It's electron degeneracy pressure, a quantum mechanical effect that holds the white dwarf up, not fusion. There is no fusion. The fires have gone out. A white dwarf generates no energy. It is simply cooling, radiating away the heat of billions of years of stellar life. And it will cool forever, growing dimmer, colder, darker, eventually becoming a black dwarf, a cold, dead cinder drifting through the void. But here's the thing. The universe isn't old enough for any black dwarfs to exist yet. The cooling process takes longer than the current age of the cosmos. Every white dwarf that has ever formed is still out there, still glowing, still fading. The first black dwarfs are still trillions of years in the future. Everything I've told you so far applies to stars like our Sun. Stars with masses below about 8 times solar. The common stars, the majority. But for the massive stars, the blue giants, the supergiants, the blazing beacons that burn so bright and die so young, the story is profoundly different. And it is here that the universe shows us what it's truly capable of. Consider a star of 25 solar masses. Such a star might spend only a few million years on the main sequence, then it begins to die. But unlike the Sun, its core gets hot enough for carbon fusion, hot enough for oxygen, hot enough for silicon. The massive star doesn't stop at carbon. It keeps going. Carbon fuses into neon and magnesium, neon fuses into oxygen, oxygen fuses into silicon and sulfur, and silicon fuses into iron. Each stage is faster than the last. Each produces less energy. The star is running out of options. Carbon burning might last 1,000 years. Neon burning, a year. Oxygen burning, months. Silicon burning, a day. The star develops an onion-like structure, concentric shells of different elements, each fusing into the next, at the very center, an iron core. And then catastrophe. Iron is special. Iron is the most tightly bound nucleus in nature. All the energy you can get from fusion, you get by making iron. Lighter elements want to become iron. It's the bottom of the nuclear binding energy curve. But this means you can't fuse iron to release energy. If you try, you don't get energy, you consume it. So when the core of a massive star becomes iron, fusion stops. There is nothing left to burn. Nothing left to generate the pressure needed to hold up the star. The core, 1.4 solar masses of iron, the mass of the Sun compressed into a ball the size of Earth, suddenly finds itself with no support. And it falls. What happens next takes a fraction of a second. The iron core collapses at 1/4 of the speed of light in milliseconds. It shrinks from Earth-sized to roughly 20 kilometers across. 20 kilometers. That's it. The mass of the Sun in a ball you could fit inside a city. The density rises to nuclear values comparable to the density inside an atomic nucleus itself. Protons and electrons are crushed together, forming neutrons. A flood of neutrinos, ghostly particles that barely interact with anything, erupts from the core. The infalling material from the outer core slams into this newly formed neutron ball and bounces. A shockwave rips outward. The neutrino flood, normally the most penetrating particles in existence, is so intense that even they deposit energy into the infalling matter. The outer layers of the star are blasted into space. This is a supernova. For a few weeks, a supernova can outshine an entire galaxy, 100 billion stars, and one dying core produces more light than all of them combined. The energy released is beyond comprehension, 10 to the power of 44 joules. The Sun's entire energy output over its 10 billion year lifetime, released in seconds, and that's just the light. 99% of the energy goes into neutrinos, a flood so intense that if you were standing 1 astronomical unit away, the neutrinos passing through your body would deliver a lethal radiation dose. Even though neutrinos barely interact with matter at all, the supernova explosion does something crucial. It distributes elements. All those shells of nuclear ash, the silicon, the oxygen, the carbon, the magnesium, are blasted outward at thousands of kilometers per second. They mix with the interstellar medium. They seed the nebulae from which new stars will form. And something else happens. In the extreme conditions of the explosion itself, temperatures and neutron densities beyond anything in normal stellar fusion, heavy elements are created. Elements heavier than iron. Gold, silver, platinum, uranium. These elements cannot be made in stellar cores. They require the catastrophic violence of a supernova or the collision of 2 neutron stars. The gold in your jewelry was forged in a cosmic explosion. The uranium in nuclear reactors was created in the death throes of a massive star. You are wearing the debris of stellar apocalypse. After the explosion fades, after the outer layers have been blasted across light years, something remains, the core, 20 kilometers across, 1.4 to 2 solar masses, a ball of pure neutrons held up by neutron degeneracy pressure. This is a neutron star. A teaspoon of neutron star material would weigh 1 billion tons. The surface gravity is 200 billion times Earth's. Drop something from 1 meter and it hits the surface at 1% the speed of light. Neutron stars spin fast. Conservation of angular momentum, compressing the original stellar rotation into a tiny volume. Some spin hundreds of times per second. And they have magnetic fields 1 trillion times stronger than Earth's. Sometimes much more. When a neutron star's magnetic axis is tilted relative to its rotation, it sweeps beams of radiation through space like a cosmic lighthouse. If Earth happens to be in the path, we see pulsars, regular as clockwork. Pulsars, nature's most precise timekeepers. But for the most massive stars, those exceeding 25 solar masses, even a neutron star is not the end. When the core mass exceeds about 3 solar masses, neutron degeneracy pressure fails. Nothing can halt the collapse. The core keeps shrinking. The density keeps rising. The gravity keeps strengthening until the escape velocity at the surface exceeds the speed of light. At that point, nothing can escape. Not matter, not light, not information. A black hole has formed. The event horizon, the boundary of no return, is not a physical surface. It's a mathematical one, a line in space-time beyond which the future contains only the singularity. And at the singularity, at the center, according to general relativity, infinite density. But we know general relativity must break down there. Infinite density is physics telling us our theory is incomplete. We need quantum gravity to understand what really happens inside a black hole. We don't have quantum gravity yet. The interior of black holes remains one of the great mysteries. So we have travelled from the cold, dark nurseries where stars are born, through the billions of years of steady burning, through the dramatic deaths, the swelling, the explosions, the collapses, white dwarfs cooling forever, neutron stars spinning in the dark, black holes swallowing everything. But death is not the end. The materials released by dying stars, the carbon and oxygen from red giants, the heavier elements from supernovae spread through space. They mix with the interstellar medium. They become part of new nebulae. And in those nebulae, gravity begins its patient work again. New stars form. around them, new planets, on some of those planets, perhaps new life. The cosmos is not wasteful. Nothing is truly lost. The iron in your blood was once in the core of a massive star. The oxygen in your lungs was fused in a stellar interior. The calcium in your bones was scattered by a supernova, collected by gravity, incorporated into Earth, concentrated by biology into the skeleton that holds you upright. You are participating in a cycle that has been running for 14 billion years. And so we return to where we started, the night sky. Those points of light scattered across the darkness. You know now what they are. Not fixed, eternal beacons, but furnaces and forges, nurseries and graveyards, objects in constant transformation, being born, burning, dying, seeding the cosmos with the raw materials for new creation. And you know now what you are. You are what stars become when they arrange themselves just right. You are stardust that has learned to wonder about stardust. The boundary between sky and self is an illusion. You are not an observer of the cosmos. You are a participant, a brief pattern of matter and energy that the universe has organized into something capable of asking questions about itself. Carl Sagan said it best: we are a way for the cosmos to know itself. When you look up at the night sky, you are looking at your own ancestry. Those stars are the factories where your atoms were forged. Some will die in the coming millions of years, scattering new elements into space, providing raw materials for worlds that won't form until long after humanity is gone. The cycle continues, indifferent to us, perhaps, but not diminished by our brevity. We exist during the stelliferous era, the age of stars, when the universe is bright with nuclear fire and the elements of life are abundant. Trillions of years from now, the last stars will burn out and the cosmos will grow cold and dark. But that is not now. Now, the universe is alive, creating, destroying, recycling. And at this moment, in this brief window of cosmic time, on a small rocky planet orbiting an ordinary yellow star, the universe has produced something extraordinary, something that can look up at the night sky and understand. In all the hundreds of billions of galaxies, each containing hundreds of billions of stars, that capacity for wonder might be the rarest and most precious thing of all. So look up, see your history, see your origins, see the violence that made your peace possible, the death that made your life possible, and feel the connection. You belong here. You are the universe, looking back at itself. And that is the most wonderful thing of all.